They're just making some discrete vessels through tissues. And then obviously we have an extracellular level. We have tissues, I mean we want to form bone. So we should all try to capture this, making it probably necessary to come up with a multi-scale model. And so that's actually what we did. And actually most of the work that I will be presenting today is actually part of this paper here. We call this model mosaic model from multi-scale model of osteogenesis and sprouting angiogenesis with lateral inhibition of endothelial cells. That's a very long name. Okay, so this is the overview of the model. So I'll try to explain in the next few slides the different, let's say, building blocks. So like I said, there is a tissue level, there is a cellular level, and there is an intracellular level. Maybe start off with the cellular level. We will define endothelial cells as discrete agents, simply because we don't think it makes sense to try to represent them as a continuum variable. For that, they are already discrete. Now, obviously, in an ideal world, you would like to represent every individual cell. The trouble is that it requires quite some computational power, as you have heard from Nena. And so, from that point of view, we, let's say, average, let's say, all the other variables. And so, we will have, let's say, a tissue level or a continuum level that are basically averaged quantities of, let's say, all the other cells, growth factors, and matrix densities. And then, of course, we have an intercellular level, and in this model, we only define an intercellular level to, let's say, govern the behavior of the endothelial cells. Obviously, in the future, you could try to extend this. And so we limit ourselves here to a number of molecules, let's say, VEGF receptor 2, because this is one of the key receptors to interact with VEGF. We also make a distinction between, let's say, the non-activated, the activated, and even the effective levels of these VEGF receptor 2. So we have obviously delta-like ligand 4, notch 1, because this is essential for our inhibitory mechanism. And we also have actin, just as a state variable. Why actin? Because actin is important actually to make it possible for the cells to move. You need to make actually a lamellipodium and a filopodia to move. Okay, before I start explaining the different components of the model, obviously we also need a domain in which you want to solve the equations. And so what we do actually is we just consider 1/4 of a healing fracture. So what you see here is actually a cross-section, so a longitudinal cross-section through a long bone. So these things here with the number 4 on, these are actually, let's say, the cortical envelopes of the bone. Here, here, and here. Here in this zone we have the number 2. This is actually where the fracture has occurred. And so, so you have basically a gap here. And this is obviously what you need to heal. Now, you will not only form new tissues inside this gap, but also, let's say, around the gap zone. And so what we do actually, so we define here this kind of funny shape, because you see that we're oversimplifying here the geometry. And this is basically the domain where we will solve our equations. Of course, if you want to solve your equations for a specific case, you also need some initial conditions and boundary conditions. And so basically we need to come up with conditions for, let's say, some cell types, like for instance the endothelial cells, so these red dots for instance, are, let's say, the initial positions of some endothelial cells from the environment. And we also need to apply some initial or boundary conditions for the growth factors for the other cells and matrix densities. Okay, start off with the tissue level. I mean, this is something that you already know from Nena's talk, because actually what we do is just writing down mass balances. So we have, let's say, diffusion reaction systems, or, well, in this case, we also add taxis terms. Because cells, they do not only migrate randomly, which you could try to capture, for instance, just by Fick's law, but they can also move in a certain direction according to certain gradients in chemoattractants, but also in matrix densities. And these processes are known as chemotaxis and haptotaxis. And so, well, what you see here is just the diffusion. These are actually the taxis terms, and these are reaction terms, because we will also try to capture proliferation, differentiation, cell death, and so on and so on. Okay, so a few more words on this continuum level. So we have a number of variables, continuum densities, accounting for bone, cartilage, fibrous tissue. We have a number of cellular variables like mesenchymal cells, stem cells, or, well, because again, we're not so sophisticated that we're making distinction between a true stem cell or a progenitor or precursor. In general, you could see this just as a source of cells that could differentiate to either osteoblasts, chondrocytes, or fibroblasts. Obviously, differentiation is something that is, among others, governed by growth factors, so we need to come up with, let's say, some generic growth factor densities accounting for osteogenic and chondrogenic differentiation, and obviously also an angiogenic growth factor. Then finally, we also need oxygen. And so what we do is we come up with functions, let's say. Well, let's say, first of all, we come up with partial differential equations that contain a number of terms, and these terms, they can be dependent on other variables. So you have a system of coupled partial differential equations. And so just to give you some idea on what these equations are all about, so you have an equation for the concentration of mesenchymal stem cells, chondrocytes, osteoblasts, and fibroblasts. The arrows here, they account for differentiation. These arrows here, these round arrows, they account for proliferation. Obviously, cells can migrate, and cells can also produce matrix and growth factors. Now, I will not show you all the details of the equations. For that, I would just like to refer to the paper. But since my title is on oxygen, I'd just like to tell you a bit more on how we capture the effect of oxygen and how oxygen actually enters in our system. And so, what you see here is just a mass balance for oxygen. Obviously, oxygen can diffuse. What we do here is just say that an endothelial cell, or let's say a blood vessel, is like a source of oxygen. But I should say that we're not taking into account. Ooh, wow, that went fast. Hold on a minute. Okay, there we go. So we're not taking into account flow. So it's just like a source term, actually. And then finally, we also add some decay term. At this stage, it's not even depending on the number of cells, so it's not really a consumption term. It's something that I'll try to elaborate a bit more by the end of the talk. And so for the rest, what do? Well, we say that actually both angiogenesis and osteogenesis are regulated by local oxygen concentrations. And so, like I said, high oxygen tensions, they actually favor osteogenic differentiation, but also hypertrophy. And so what we do is we actually define rate terms that account for the rate of differentiation. And we define here these Hill functions that actually make sure that indeed if you go to low, so you basically have like a switch-like behavior. There's like a threshold somewhere. And so if you go below this threshold, actually osteogenic differentiation, but also endochondral ossification will basically decrease. We do something similar actually for VEGF expression. So again, we define this kind of functions here that again account for a switch-like behavior. It basically says, well, if you go below a certain threshold, the expression of VEGF will basically increase. And this is the case for both osteoblasts and also these hypertrophic chondrocytes. I also need to tell you a bit more about how we actually implement the movement of endothelial cells. So what we do is actually we just define a velocity, and a velocity is nothing more than, let's say, a magnitude times a unit vector. And we come up with equations that, first of all, make the velocity of this tip cell dependent on the activation of VEGF receptor 2, which makes sense indeed. And for the direction, we say, well, it's actually like a weighted average of chemotaxis and haplotaxis. So these are actually things that are calculated at the tissue level. Now this is for, let's say, tip cells that are already a tip cell, but we also need to come up with a criterion to say when is an endothelial cell actually able to become a tip cell. And so what we do is, well, we define actually two conditions or two criteria. One that has to do with, let's say, a minimum level of VEGF receptor 2 that has to be present, and the second one has to do with, let's say, the threshold for the actin level that also needs to be exceeded in order to become a tip cell. So then the intracellular level. So this has to do with this inhibition mechanism. So this is actually something that we basically took over from the work of Katie Bentley. And so basically what we say is, well, the level of activated VEGF receptor 2 is proportional to the local VEGF concentration. Then once VEGF receptor 2 gets activated, it leads to an increase in the level of delta ligand 4. And finally, we have another algebraic equation which basically says that VEGF receptor 2 levels will actually get downregulated upon Notch1 activation. And then finally, what we also say is that actin gets upregulated upon VEGF receptor 2 activation. So let's have a look at some of the results now. So these are, well, first of all, what do you see here? You see actually the formation of a blood vessel network, and how this is actually related to local VEGF concentrations and oxygen. And so what you can hopefully appreciate from these animations is that in areas of low oxygen concentrations, which are actually light gray, you will have high concentrations of VEGF, and this will obviously create gradients that actually attract the blood vessels. Once the blood vessels come in, it will basically lead to a decrease in oxygen, an increase in oxygen. As a result of that, VEGF expression levels will reduce. We can also have a look at how tissue densities change as a result actually of the formation of blood vessels. So what you see here actually is that, this is bone, this is cartilage, this is fibrous tissue, that actually most of the bone is formed in an indirect way, meaning that first cartilage is being formed, which is then gradually being replaced by bone. Apart from some areas here in this area where you have direct bone formation. Now obviously, I mean, this is a model which is quite complicated in the sense that we have actually I lost counting, but I think we have about 50 to 100 parameters, so it's quite a lot of parameters. You should, of course, do some model calibration to make sure that actually you predict some of the experimental dynamics. And so what we've done here is actually compare the tissue fractions in different areas of the healing bone and make sure that our predictions actually match the ones from the experiment. Now, I mean, this is nice, but of course we're not only interested in just describing only the reality, we want to do something useful with that. And so one of the things we can do now is actually see whether there is some relation between, let's say, a certain genotype and a certain phenotype. And so what we can actually do now is do simulations of over and under expression of certain molecules. Like, for instance, over and under expression of delta ligand 4. And so what you see in the under expression case, you will have more blood vessels. Oops. Come on. While in the overexpression case, you have less blood vessels. And this makes sense, of course, because if you have less delta-like ligand 4, you will have less inhibition, and as a result of that, you will have more tip cells making more vessels. And this is also something that has been reported in the literature. Now, what you can also do now is see to what extent this leads to a so-called bone phenotype, or in other words, whether this could actually also lead to enhanced or retarded healing. And so what you see here, for instance, are a number of results in terms of tissue fractions. First for the normal case, then for a delta-like ligand 4 overexpression case, and then a case where we actually overexpress VEGF. And so what you see here is that actually for this delta-like ligand 4 overexpression case, there is not so much of a difference, because these curves here, they're actually quite similar, while for VEGF there is clearly a strong effect, and so bone gets formed much faster. Now this was a case where we only slightly increased VEGF expression. The interesting thing was, if we keep on increasing VEGF, at some point actually the vasculature is actually not fully recovered. And so these vessels, they just stop at some point. And obviously it also leads to a non-union. Now, how is this possible? I mean, obviously there may be many mechanisms, and the only mechanism we can come up with is a mechanism that is introduced in the model. And in our case, it's actually related to